Electricity transmission has 3 steps. First, generation. Power plants make electricity by burning fuel or other methods. Next, transmission. Electricity is raised to higher voltage and sent to the area through high voltage lines. Finally, distribution. Electricity is lowered and sent to homes, factories through low voltage lines. But why don't we just transmit electricity directly, instead of first increasing the voltage to hundreds of thousands of volts? We know wires have resistance, and electric current is created by moving electrons. As electrons flow through the wire, they collide with atoms, generating heat and causing energy loss. According to Joule's law, the energy lost equals the square of the current times the resistance. If the wire's resistance stays the same, the only way to cut energy loss is to lower the current. But to deliver the same power from the station to users with less current, we must raise the voltage, since power equals voltage times current. So, voltage is increased to reduce energy loss in long-distance transmission. Let's look at how this process works. Generators at power stations output voltages from 6000 to 20,000 volts. After generation, it goes through a step-up transformer, raising the voltage to 220,000, 500,000, reaching ultra-high voltage levels. After being stepped up, electricity travels through high-voltage lines from the power station to other regions. At substations, the voltage is lowered to 110,000, 66,000, or 35,000 volts, then distributed to homes, businesses, and other areas. As electricity reaches the end user, the voltage must be reduced by a low-voltage transformer to 380 or 220 volts, making it suitable for homes and small commercial equipment. So, how is this voltage change achieved? It's done using transformers, the core equipment in substations. Whether it's a small transformer in electronics or a large one in an ultra-high voltage substation, they all work on the same basic principle: Faraday's law of electromagnetic induction. When a magnet moves near a coil, the changing magnetic field causes electrons to move, generating electric current. Increasing the magnet's speed or adding coils raises the voltage. A transformer has an iron core, a primary coil, and a secondary coil for AC. When AC flows through the primary coil, the changing current creates a changing magnetic field. The changing magnetic field goes via the iron core to the secondary coil. By Faraday's law, changing magnetic flux induces voltage in the secondary coil. According to Faraday's law and the turns ratio, output voltage is proportional to input voltage and coil turns. By changing the turns ratio between two coils, voltage can be increased or decreased. Power plants usually generate 3-phase electricity, needing 3 sets of iron cores. To save space, 3-phase transformers wind both primary and secondary coils onto the same iron core. The iron core thickness is designed to be as small as possible, and materials like silicon steel are used to enhance magnetism. However, some energy loss is inevitable when a transformer operates, mainly as heat. To reduce this, the inside is usually filled with insulating oil. This helps conduct electricity and cools the system. The insulating oil removes heat by convection, with extra cooling from external radiators.